Today we'll study two different algorithms to train linear classifiers. But before we study linear classifiers, let's first consider decision trees. In the first class of this series, we studied decision trees. Decision trees can be very intuitive and also useful in certain cases. But there's a simple example in which decision trees are not suitable, and that's the majority vote function. Suppose we want a function that returns 1 if the majority of our attributes are 1 and -1 otherwise. So we have n binary attributes, which means every example is a vector of n values, where each value is either 0 or 1. And if the majority of these xi's are 1, then the function should return 1 and -1 otherwise. If you're to build this function using decision tree, what would it look like? Well, you can do something like this. So at the root, you consider the first attribute, see if it's 0 or 1. And then you look at the second attribute, see if it's 0 or 1. And you keep doing this and go through all the attributes, and the leaves will have values -1 or 1, depending on the number of ones in the path to the given leaf. Rightmost path would lead to 1. For something as simple as identifying the majority of a vector, you need a full tree if you're to use a decision tree. Let's study linear classifiers using spam filtering as an example. So we want to build a classifier that can identify spam emails. And we've defined 5 features. Does the email contain the word Viagra? Does it contain the word learning? Does it contain the word the, dating, and Nigeria? And suppose we have 3 emails, 1, 2, and 3. And each email has classification 1 for spam and -1 for not spam. It's a very small data set, but we can see that words like Viagra and Nigeria are associated with the email being spam, whereas the word learning, or perhaps not having the words Viagra or Nigeria, is associated with the email not being a spam. And the word the doesn't really tell us much. So intuitively, we want to check if the email contains the word Viagra or Nigeria. If they do, we want to increase the chance of it being a spam, whereas if it has the word learning, we want to decrease the chance of the email being spam. And that's a high-level idea. And how do you formulate this mathematically? The simplest way would be to define what's called a weight vector and take the dot product of that and our email vectors. For example, if we take the dot product between the weight vector and the first email vector, then we have 1 plus 0 plus 0 plus 0 plus 0, which is 1. And the sign is positive. On the other hand, if we take the dot product with x2, then we would have 0, -1, 0, 0, 0, which is -1. So the sign is negative. Once we define the weight vector in a meaningful way, we can just take the dot product between the weight vector and the email vector and look at the sign, whether it's positive or negative. And this type of classifier is called the linear classifier because we're taking a linear combination of the values of the input vector. For this simple example, we can just use 1s, 0s, and -1s, but we could have used real valued weights. Say, we're really sure that if the email has the word Viagra, it's just spam, and say we're half as confident if it has the word Nigeria, and so on. And visually, it looks like this. Here's our unit vector, and this dotted line is a collection of all vectors where the dot product is 0. Say our weight vector is -1, 1. If x were 1, 1, the dot product is 0, so we wouldn't know how to classify it. But if x were 1, -1, the sign of the dot product is negative, so we can classify it as not spam. And for something like -2, 1, the sign of the dot product is positive, so we'll classify that as spam. So by taking the dot product of the weight vector and the data point and looking at the sign of it, we can determine whether it's a spam or not. We can also introduce this notion of bias. So instead of just taking the dot product, we can also add a bias. And visually that amounts to moving up the boundary between the positive and negative class. And notice that the positive and the negative class have a linear boundary. And that's another reason why these are called linear classifiers. As a recap, linear classifiers classify data points by taking the dot product between the weight vector and the data point and adding a bias and then considering the sign of it. When we say we train a linear classifier, we mean to identify a weight vector out of all n-dimensional vectors and a bias out of all real numbers, such that the combination gives the best results when it comes to classifying instances correctly. And we'll study two different algorithms to identify the weight vector and the bias. The first is a simple algorithm called perceptron. And here's how the algorithm works. Let's first forget about k, which keeps track of how many times the weight vector has been updated. And suppose we have n data points. So this for loop means do this for all n examples. And what do? If this condition happens, you update the weight vector. The dot product, as you know, is a prediction or classification using the kern W. And y is the true class of the example, which is either -1 or +1. If the true class and the predicted class are the same, the product will be positive. So the if condition is saying if the prediction is wrong. If the prediction is wrong, then update the weight vector. And how do we update the weight vector? Let's forget about eta for now. All we're doing is we're adding y times x to w. So if you think back at the spam example, suppose we have an email that contains the word Viagra, but the classifier wrongly classified it as -1, so not spam. By adding x to y, now w has a heavier weight for Viagra. And same thing for the word learning. Suppose this classifier wrongly classified a non-spam email containing the word learning. And this time y is negative because it's a non-spam email. We're adding the negation of x, which means we give a negative weight to the word learning. And eta is a learning rate. Which controls how fast the weight vector changes. And then lastly, if we bring back k, then we can keep track of the change of the weight vector, though it's not really necessary. We just need the final weight vector. And this is repeated a fixed number of times, or until convergence. Let's look at an example. We want to train our linear classifier using 4 data points, and we initialize our weight vector to all zeros, and we use this weight vector to classify our first data point, and the dot product is 0, whereas the true class is 1. This is incorrect. So we update w by adding eta times the true class times x1 vector to the weight vector. So our new weight vector is 1, 2. So this is our new weight vector, which means after looking at the first example, our decision boundary looks like this, positive and negative. And we look at the second example, and when we take the dot product, we get a positive value, and the true class is also positive, so it's correct. So we don't update our weight vector. When we look at the third example, we take the dot product, which gives us a negative value, and the true class is also negative. So the classification was correct. So we don't update the weight vector. When we look at the fourth example, the dot product is 1, whereas the true class is -1. So now we have to update the weight vector, and we do the same thing as before. We add eta times y4 times x4 to our weight vector, which results in a new weight vector of 2, 1. So after looking at the fourth example, this is our new weight vector, meaning now this is our decision boundary. Everything to the right of this is positive, and to the left of it is negative. And you keep doing this a fixed number of times or until the weight vector doesn't change. And now we'll look at support vector machines, or SVMs. Okay, let's start with the simplifying assumption that our data points are linearly separable. And there can be many different decision boundaries, h1 through h4 for example, and they're not equally good. We somehow think that a good boundary would be somewhere here, and a data point that falls right here should be classified as positive. But if we use h1 as a boundary, then it would be classified as negative. So the question we're trying to address here is, given a linearly separable data, how do we identify a boundary between two classes that's optimal? One way to define and quantify the optimality of a hyperplane is to consider the distance between the hyperplane and the nearest points. And we can call this distance delta. And the bigger the delta, the better the hyperplane is. So h1 has a very small delta, and so does h2, h3, and h4 if you compare that to h star. And mathematically, this margin delta of an example is just the class of it multiplied by the true class. And this is how we identified whether an example was correctly classified in perceptron algorithm. And sometimes we call this the functional margin. And once you define the functional margin of an example, then we can define the margin of a classifier on some data as the minimum of these. And you may notice that the hyperplane is defined only by the nearest vectors, and these are called support vectors because they support the hyperplane, and that's where the name support vector machines come from. And none of these really matter. Again, the goal is to find a hyperplane with the largest delta, and the hyperplane is defined by the weight vector and the bias we choose. And as you know, the delta we're trying to maximize is the dot product between the weight vector and x and bias. And since we can choose a weight vector, delta can get arbitrarily large if we just make our w bigger and bigger. So we want to somehow constrain the weight vector. So we're not just maximizing delta, but we're also constraining the weight vector. And we can get the same effect by constraining delta and minimizing the weight vector. And we'll approach it this way. So we'll fix delta to a fixed value, say 1, and then minimize w. What we just discussed can be formalized as a optimization problem as follows. Again, we're trying to minimize w, which is the same as minimizing 1/2 times w dot w. But it makes the math work out easier. And we're fixing the delta to a specific value 1. And this is the delta of each point. So we're minimizing w while every point is at least 1 away from the hyperplane. Visually, this distance is 1. This delta is 1. So the distance between any point and the hyperplane is at least 1. So one assumption we made is that the data points are linearly separable. Is this a good assumption? Well, it's not. Firstly, we have cases where the examples are not linearly separable. There's no line that can separate positive examples from negative examples. Or in some cases, the separating hyperplane may not be an optimal hyperplane. So we would think that this point is noise and that this would be a better hyperplane. To handle both of these situations, we introduce a notion of slack. And the slack of a point is how far off the point is from the correct side. And all these points are on the right side, so they have 0 slack. And so are these. And if we had a point here, even though it's on the correct side of the boundary, we still have a non-zero slack. This is what we had before. When you introduce the slack, the condition becomes every point has to be at least 1 away from the hyperplane to every point has to be 1 minus slack away from the hyperplane. And the slack is defined as non-negative. And the optimization is still minimizing W while also minimizing the sum of the xis. And C determines sensitivity to slack. So visually now we can have data points that are on the wrong side or within 1 from the hyperplane. So C sets the sensitivity to slacks. So then when C becomes large, which of the following would be the case? The answer is A, because if you increase C, then every non-zero xi has a bigger impact on the whole value, and we're trying to minimize this whole value. So as C gets bigger, you're penalizing non-zero xi's more severely. A second question for you is the sum of xi's an upper bound on the number of training errors? The answer is A, because training error means that the point is on the wrong side of the hyperplane, which means the given xi is greater than or equal to 1. So for every training error, you'll have a xi that's greater than or equal to 1. So if you sum up the xi's, then the number will be bigger than the number of training errors.